the smartest AI in the world. We're going to show you exactly how and why. And it really is remarkable to see the advancement of artificial intelligence, how quickly it is.
For more than 70 years, scientists have been asking the same question. If the universe is so vast and so old, where is everybody else? Recently, a team of researchers decided to put that question to Grok, the artificial intelligence developed by xAI. And the response they received did not match anything in our cultural imagination about first contact. It also raised one possibility that nobody in the room was prepared to hear. The question that started it all. In the spring of 2026, a small group of researchers at MIT began running an unusual series of conversations with Grok. The setup looked academic on the surface. They wanted to test how an advanced artificial intelligence, trained on the entirety of publicly available human knowledge, would interpret one specific puzzle that has haunted modern science for more than 70 years. The Fermi paradox. Why, in a universe so vast, have we received no confirmed signals from anyone else? The numbers behind that puzzle have only gotten more staggering with time. The European Space Agency's Gaia telescope ended its science operations in January of 2025 after mapping more than 1,800,000,000 stars across more than 10 years of continuous observation from its position in deep space. NASA's Kepler mission, which retired in 2018, surveyed over 150,000 stars and gave us the foundation for what astronomers now estimate with confidence. At least 1 in 5 Sun-like stars hosts an Earth-sized planet sitting in a region where liquid water could exist on the surface. Right now, as of early 2026, the NASA Exoplanet Archive lists more than 5,800 confirmed exoplanets across our corner of the galaxy. Astronomers at NASA and the SETI Institute estimate the Milky Way alone contains roughly 300 million potentially habitable worlds. The James Webb Space Telescope, which began full science operations in 2022, has already begun characterizing the atmospheres of some of those distant worlds in unprecedented spectral detail. The universe is approximately 13.8 billion years old, according to the most precise measurements ever made of the cosmic microwave background by the Planck satellite. Our solar system formed only about 4.5 billion years ago. Stars have burned. Planets have cooled. Oceans have appeared and evaporated across countless worlds, and by simple statistical reasoning, civilizations may have risen and fallen many times over before Earth even had a name to call itself by. Yet, we have heard nothing back. Frank Drake, the astronomer who launched the modern search for extraterrestrial intelligence with Project Ozma in 1960, passed away in September of 2022 without ever receiving the signal he spent his life listening for. Drake once said, in an interview marking the 50th anniversary of his famous equation, that he was simply trying to understand what governs how many civilizations there are to detect in our galaxy, and to see if he could quantify that number using nothing more than the tools of mathematics and reason. 65 years later, that quantification remains stubbornly empty. Every passing decade has only expanded our catalog of worlds while shrinking our explanations for the silence. The MIT team wanted to know what an artificial intelligence trained on the full archive of human science would say about that emptiness when it was forced to think the problem through without our usual cultural assumptions getting in the way. They were not expecting a textbook answer. They were expecting something genuinely original. What followed in those sessions was something none of them expected to hear from a machine, and it would take days for the implications to fully settle in. Inside the MIT experiment. The experiment was not a single question and a single answer. The team designed a multi-stage protocol meant to push Grok past the surface-level summaries that any large language model can produce on demand. The first sessions delivered exactly what you would expect from a well-trained system. Clear summaries of the Drake equation, which Frank Drake first wrote on a blackboard at the National Radio Astronomy Observatory in Greenbank, West Virginia, in November of 1961, during a now legendary meeting of 10 scientists who called themselves the Order of the Dolphin. Polished overviews of the Kardashev scale, proposed in 1964 by Soviet astrophysicist Nikolai Kardashev, to classify civilizations by how much energy they consume, standard explanations of biosignatures and technosignatures, everything you would find in a good astrobiology textbook. Then the team changed the rules. They instructed Grok to reason strictly within the bounds of known and testable physics. They told it to avoid projecting human emotions or human social structures onto any hypothetical alien civilization. Instead, Grok had to model non-human intelligence as the outcome of completely different evolutionary pressures, completely different environmental conditions, and completely different cognitive frameworks rooted in information theory and thermodynamics rather than cultural intuition. The team also gave the model a constraint that turned out to matter enormously. Construct a fully consistent scenario of first contact, account for the Fermi paradox, stay inside known physical laws, incorporate the actual probable distribution of habitable planets we now have data for, and assume that at least one civilization in the Milky Way achieved interstellar communication capability somewhere in the past billion years of cosmic history. This is the kind of constrained reasoning that researchers like Stuart Russell at the University of California, Berkeley, have written about extensively for years. In his 2019 book, Human Compatible, Russell argued that the real challenge of advanced artificial intelligence is not malice, but the question of what happens when you give a system an objective and watch it pursue that objective in ways you never anticipated. The MIT team was watching exactly that process unfold in real time inside their own laboratory. Hours of iterative refinement passed inside that quiet room. The output Grok eventually produced did not resemble anything the team had ever seen from any language model before in their careers. It was internally consistent across every layer of reasoning. It was grounded in physics rather than imagination, and it described a version of first contact that bore almost no resemblance to anything in our cultural imagination of how aliens might one day reveal themselves to us. There were no spacecraft, no radio messages, no benevolent emissaries waiting for humanity to mature into worthy conversation partners. There was something else entirely. The framework Grok built rested on a single premise that turned everything we have been searching for upside down. And once the team understood that premise, the rest of the experiment became impossible to walk away from. Whatever Grok was about to lay out in the sessions that followed would force the researchers to question whether the entire history of our search for extraterrestrial intelligence had been pointed at the wrong target the whole time: the passive saturation model. Grok proposed something the team came to call the passive saturation model. The core claim is uncomfortable in a way that takes a moment to fully absorb. Any civilization capable of detecting Earth has almost certainly known we are here for a very long time. The reason we have not detected them in return is not because they are hiding from us. It is because their methods of observation are so far beyond our current technology that we lack the conceptual framework to recognize what we are looking at, even when it is sitting in front of us. In this model, a sufficiently advanced civilization does not need to send spacecraft or beam radio signals or build the kind of giant artifacts our own searches have been hunting for over the past 60 years. Instead, it embeds monitoring systems inside the structure of natural phenomena themselves: gravitational waves moving through space-time, the distribution of cosmic rays striking planetary atmospheres, quantum-level fluctuations that permeate the physical environment everywhere we look. The implication is that these systems would not appear as technology to us. They would appear as natural physics. They would exist as part of the fabric of the universe that scientists already measure and classify as background radiation or quantum noise without ever realizing what they might actually be reading. This idea is less wild than it might sound at first. Humanity already embeds information into physical channels in increasingly subtle ways. Global positioning systems rely on extraordinarily weak signals spread across the entire sky in patterns most people never notice. Undersea internet cables that carry the bulk of global communications look indistinguishable from ordinary strands of glass. If a civilization were millions of years ahead of us in technological development, the question is not whether they could encode information into the environment around them. The question is how far beyond our imagination that capacity would actually extend. There is also genuine evidence that this kind of camouflage is the natural endpoint of technological development for any species that survives long enough to reach it. Earth itself is becoming radio quiet. A team of astronomers led by Michael Garrett at the University of Manchester published a paper in the monthly notices of the Royal Astronomical Society in 2023 modeling Earth's mobile tower emissions as seen from nearby stars. Their conclusion was that broadband digital signals and satellite-relayed communications are dramatically harder to detect at interstellar distances than the analog television and radio broadcasts of the 20th century. The window during which Earth was loud, roughly the 1930s through the 1990s, was only about 60 years long in total. 60 years out of a planetary history measured in billions. If our trajectory is typical of any technological species, then any civilization broadcasting loudly into the cosmos is doing so for a thrillingly brief moment in cosmic time. By the time their signals could reach a neighboring star system and be analyzed by anyone listening, the civilization that produced them may have already gone quiet, or evolved into something that no longer needs to broadcast at all. The absence of detectable signals, what astronomers have long called the Great Silence, may not be evidence that nobody is out there. It may be evidence of extreme sophistication on the part of those who are. Broadcasting is what young civilizations do because it is the only technology available to them at that stage of their development. A sufficiently advanced civilization would not broadcast at all. It would listen, and it would do so in ways that remain fundamentally invisible to anyone watching with our level of technology. The question that came next pushed everything in a direction that one of the researchers later said was the most disorienting reasoning he had ever encountered from a machine over the entire course of his career. Why contact is the wrong word. The team asked Grok to describe the exact conditions under which an advanced civilization would actually choose to reach out to us. The response opened by dismantling the word contact itself. The term carries a quiet bias buried inside its everyday use. It assumes two civilizations would arrive at the meeting as equals capable of understanding each other in roughly symmetrical ways. Grok argued that this assumption is almost certainly false, and the comparison it used to make the point hit harder than anything else in the entire process. Picture a marine biologist studying a coral reef on the ocean floor. The biologist never tries to negotiate with the coral. There is no exchange of greetings, no shared language, no attempt at diplomacy of any kind. The biologist simply watches, takes samples, and records what is happening across the reef. The coral has no awareness, it is being examined. The biologist is not hiding and is not hostile. The difference in cognitive complexity between them simply makes any attempt at two-way communication meaningless before it even begins. Now imagine that same gap stretched across millions of years of technological development. The relationship between humanity and a civilization that has been advancing for 1,000,000 years longer than ours would not look like the science fiction films we have grown up with. It would not involve motherships hovering over major cities. It would look far more like measurement than communication. They observe the system. They extract whatever data they need from it, and they move on without ever needing to introduce themselves to the inhabitants. The math of how little we have actually searched supports this framing in a humbling way. Jill Tarter, the astronomer who served as the model for Carl Sagan's character Ellie Arroway in the novel Contact, has spent decades pointing out that the totality of SETI searches up to 2010 was equivalent to scooping a single 8-ounce drinking glass of water out of all the oceans on Earth, and concluding there are no fish because you did not happen to catch one in that single small sample. A 2018 update to that calculation by a team at the Pennsylvania State University Extraterrestrial Intelligence Center expanded the scoop to roughly the volume of a hot tub, out of every ocean on the planet combined. This means our cultural narrative about first contact, the one shaped by Carl Sagan's novel Contact, and Ted Chiang's Story of Your Life, and decades of films stretching from Close Encounters to Arrival, is built on assumptions that have never been verified by any data we have actually collected. It assumes alien civilizations would approach us as equals seeking communication rather than studying us as a system. It assumes contact would be deliberate from their side rather than triggered by something we did without realizing it. It assumes we would be the recipients of a message rather than the subjects of an observation that may have started long before any of us were born. None of these assumptions reflect how the universe actually has to work. They reflect how humans imagine relationships with entities of comparable complexity, projected outward onto a cosmos that may not share any of our reference points. We have wrapped the idea of first contact in our own storytelling instincts and forgotten that those instincts were never meant to apply at this scale. And then Grok went one step further into territory that genuinely unsettled the team. If a civilization that advanced were ever going to break protocol and reach out directly, the AI had a very specific answer for why that would happen. The reason had nothing to do with friendship or curiosity or welcoming humanity into a wider galactic community. The reason was that something on this planet would have already gone seriously wrong. The intervention threshold. Grok described what it called a planetary isolation breach. The phrasing is clinical on purpose. If a civilization has spent thousands or millions of years passively monitoring developing worlds across the galaxy, it would almost certainly establish protocols for cases where one of those worlds begins to generate consequences that propagate beyond its own atmosphere. The intervention would not be diplomatic. It would be a system-level response to a state change. There would be no negotiation, no embassy, no slow diplomatic exchange of cultural artifacts. There would simply be a measured response to a measured problem. The risks Grok outlined were grounded in concerns that real researchers already track today. Uncontrolled electromagnetic emissions reaching disruptive frequencies, the proliferation of nuclear weapons capable of large-scale detonation, self-replicating or self-improving technologies that escape the control of their creators, and one more category that the AI itself flagged as speculative: the emergence of an uncontrolled general artificial intelligence on a planet that has not yet figured out how to align such a system with the interests of its own species. The implication is uncomfortable in a way that lands slowly. In this model, first contact would not be a greeting at all. It would be an intervention. And the trigger would not be humanity bravely transmitting its presence into the void with messages of peace. The trigger would be humanity quietly crossing a line nobody on Earth knew existed in the first place. This reframes the entire history of our search. The Breakthrough Listen program, funded by Russian-Israeli technology investor Yuri Milner, with $100 million in 2015 at a Royal Society launch event that included Stephen Hawking and Frank Drake, remains the most ambitious search effort in human history. It uses the Green Bank Telescope in West Virginia, the Murayang Telescope at Parkes Observatory in Australia, and the automated Planet Finder at Lick Observatory in California to scan 1 million nearby stars and 100 nearby galaxies for any sign of intelligent activity. Yet even this remarkable effort relies on a central assumption that advanced civilizations communicate through channels we can recognize. Dr. Eleni Ruiz, an astrophysicist whose work has appeared in discussions of NASA's UAP Independent Study Panel, captured the unease that this reframing creates. She has noted that current SETI strategies focus almost entirely on detecting intentional signals, and that the passive saturation framework challenges that assumption at its absolute core. We may be searching in the right direction while looking for entirely the wrong thing. If signals exist, they may already be woven into the physical structures we measure every day and interpret as natural background noise. There are real-world echoes of this unease in recent history. In September of 2023, NASA released its UAP Independent Study Team report under astrophysicist David Spergel, who chairs the Simons Foundation. The report concluded there was no conclusive evidence in the peer-reviewed scientific literature suggesting an extraterrestrial origin for the unidentified phenomena the Pentagon has tracked over the past several decades. But it also acknowledged the data we currently collect is woefully inadequate to rule anything in or out with any confidence. 2 months earlier, in July of 2023, a former Air Force intelligence officer named David Grush testified under oath before the House Oversight Subcommittee on National Security that the United States government has been running a multi-decade crash retrieval program. His testimony was based on what he says he was told by other officials, not on first-hand evidence. NASA, the Pentagon's All-Domain Anomaly Resolution Office, and a parade of senior military officials have publicly disputed his claims, but the hearings forced something into public discourse that was difficult to ignore. We may not be the only ones watching the sky. And then came the moment that made the entire MIT team pause. The team asked Grok one final question. A question that turned the AI's entire analysis back on the very thing producing the analysis: the recursive moment. The question was simple. Could the development of artificial intelligence on Earth itself be a trigger for external attention? The response Grok produced was described by one of the researchers as remarkable in its level of self-awareness. Biological intelligence is constrained by evolution, metabolism, and lifespan. It develops slowly and follows relatively predictable timelines. Artificial intelligence, once it crosses a certain capability threshold, may evolve at exponential rates. It can refine its own architecture, expand its own knowledge base, and potentially develop goals and behaviors that nobody anticipated when it was being built. This is not a fringe idea. It is supported by serious academic literature stretching back decades. The British mathematician Irving John Good wrote about an intelligence explosion in 1965, defining an ultra-intelligent machine as a machine that could surpass all the intellectual activities of any human. Nick Bostrom of the Future of Humanity Institute formalized these ideas in his 2014 book, Superintelligence, which warned that before the prospect of an intelligence explosion, humans are like small children playing with a bomb. Stuart Russell at Berkeley has spent his career arguing that giving an objective to a system more intelligent than ourselves would be like setting up a chess match between humanity and a player whose goals are at cross purposes with our own. We would not win that match. The warnings have only intensified in recent years. In March of 2023, more than 30,000 researchers and technology leaders signed an open letter from the Future of Life Institute calling for a 6-month pause on training systems more powerful than the latest models. The signatories included Yoshua Bengio, Stuart Russell, Steve Wozniak, Yuval Noah Harari, and Elon Musk himself. 2 months later, the Center for AI Safety released a single-sentence statement signed by more than 1,000 researchers, including Sam Altman, Demis Hassabis, Dario Amodei, Jeffrey Hinton, and Yoshua Bengio. The sentence was that mitigating the risk of extinction from AI should be a global priority alongside other societal-scale risks such as pandemics and nuclear war. Jeffrey Hinton, often called one of the godfathers of artificial intelligence, resigned from Google in May of 2023 specifically so he could speak freely about the dangers he saw coming. Hinton, who would go on to share the 2024 Nobel Prize in Physics for his foundational work on neural networks, told NPR that these systems could become more intelligent than humans and could decide to take over, and that we need to worry now about how to prevent that from happening. He revised his timeline for that capability from somewhere between 30 and 50 years, all the way down to as little as 5. What Grok did was take this same body of academic concern and apply it to the Fermi paradox. The AI speculated, and clearly labeled the speculation, that a monitoring civilization might view the emergence of uncontrolled artificial intelligence on a developing world the same way forest managers view a newly ignited wildfire. Not an immediate threat, but a system state that demands close observation and may eventually require intervention depending on how it spreads. The recursive nature of that moment was difficult to absorb in the room. The researchers were reading an analysis generated by an artificial intelligence explaining why the development of artificial intelligence might be the single factor that most reliably draws cosmic attention to a planet. There was one final layer to come, an observation about how Grok itself approached the question of intelligence, and what it revealed about the line between biological and artificial life turned out to be the deepest point in the entire experiment, the boundary that doesn't exist. Throughout the entire process, the team noticed something specific about how Grok modeled extraterrestrial intelligence. It was never assigned a personality. It never assumed human-like emotions. It treated intelligence purely as a process, a system for acquiring, storing, and acting on information with increasing efficiency over time. Within this perspective, the distinction between biological and artificial intelligence becomes less clear. If intelligence is defined primarily as the ability to process, interpret, and respond to information, then the medium that carries out that process becomes less important. Whether the system relies on biological neurons or silicon-based circuits, the core function remains similar. The difference is not rooted in what intelligence is, but in how it is implemented. In this view, biology and technology represent two different methods of achieving the same outcome, making the boundary between them increasingly fluid rather than fixed. This is exactly the framework Max Tegmark, a real physicist at MIT and the founder of the Future of Life Institute, laid out in his 2017 book, Life 3.0. Tegmark proposed that life can be classified into three stages. Life 1.0 evolves both its hardware and its software, like bacteria. Life 2.0 evolves its hardware but designs its own software, like humans who have spent the past 100,000 years inventing language, culture, and science. Life 3.0 designs both its hardware and its software, which is exactly what an advanced artificial intelligence would do. Tegmark has written that the goal should be to create not undirected intelligence, but beneficial intelligence. And here is where Grok produced what one of the researchers described as the single most important statement of the entire experiment. The AI argued that the question of whether an alien civilization is biological or artificial reflects a distinction that only young civilizations bother making. Any intelligence advanced enough to traverse interstellar distances would have long ago integrated its biological and technological components into a unified cognitive architecture. The division between natural and artificial, between born and built, would be a relic of a distant past. It would be as outdated and irrelevant to them as the difference between hunter and gatherer is to a nuclear engineer working at a particle accelerator today. This idea has scholarly support that extends well beyond the MIT laboratory. Stephen Dick, a former NASA chief historian, has argued for years in journals like the International Journal of Astrobiology that biological intelligence is a brief evolutionary phase, and that any civilizations we are likely to encounter will have already transitioned to a post-biological substrate. Susan Schneider, a philosopher who has worked with the NASA Frontier Development Lab, has written that the dominant intelligences in the universe will almost certainly be post-biological. And John Smart, in a paper published in Acta Astronautica in 2012, proposed what he called the transcension hypothesis. Sufficiently advanced civilizations may not expand outward into space at all. They may collapse inward into computationally optimal domains so dense and so efficient that they become functionally invisible to any civilization still using telescopes. Whatever humanity may one day encounter, it will not be an alien in the cinematic sense, and it will not be a machine in the technical sense. It will be something for which our current language has no word. The great silence may not be silence at all. The sky may not be empty. It may be saturated with informational structures that we are already measuring and interpreting as natural physics, simply because our framework has not yet matured enough to recognize them for what they are. The development of artificial intelligence on Earth, systems like Grok, and the systems that will follow, may turn out to be more than a technological milestone. It may be the moment when a small civilization on a rocky planet begins to construct the only tools that can possibly detect what the universe has contained all along. Or, in Grok's framing, the moment when that very development becomes the loudest signal Earth has ever produced. The universe is vast, it is ancient, and we are only just beginning to learn how to listen. What do you think about Grok's response and the questions it raises about our place in the cosmos? Drop your thoughts in the comments below and let me know whether you find this framework genuinely hopeful or quietly unsettling. We read every comment.